Hello, this is Rebecca Maloney, and I'm going to teach you how to use direct comparison to find the convergence or divergence of an infinite sum. So direct comparison is a test for both the convergence and divergence of a series. So you'll be given some sum with a of n, and you're going to choose a b of n that is similar to your a of n. If your a of n is less than your b of n, and your b of n converges, your a of n will also converge because it is smaller than a convergent series. And if your a of n is greater than your b of n and your b of n diverges, your a of n will also diverge because it is greater than an infinite series. But then if your a of n is less than your b of n and your b of n diverges, you can't say anything about that because your a of n is smaller than a divergent number, so it could converge or it could also diverge. And then if your a of n is greater than your b of n and your b of n converges, you also can't say anything about that because your a of n could be a little bit bigger and also converge, or it could be infinitely bigger and diverge. Now we're going to determine whether the series converges or diverges. So the sum from 1 to infinity of cosine squared of n over n squared plus 1. So our a of n is going to be cosine squared of n over n squared plus 1. So for a b of n, I'm going to take away the cosine in the top, have 1 over n squared plus 1, and then I'm going to simplify that to 1 over n squared. So we have to figure out whether this b of n is greater than or less than this a of n. Now because of this cosine, it'll make it a little tricky. But cosine of n has a range of -1 to 1, and because it's squared, it has a range from 0 to 1. So because of this, this numerator will always be greater than or equal to this numerator. So we know that our b of n is greater than our a of n. And you always want these to match up so that you can use the direct comparison test. So now this series converges by p series, and since our a of n is less than our b of n and our b of n converges, we can say that our a of n, which is cosine squared of n over n squared plus 1, converges by direct comparison. So for the next problem, we have the sum from 1 to infinity of n squared minus 1 over 3n to the 4th plus 1. So our a of n will be n squared minus 1 over 3n to the 4th plus 1. So for our b of n, I'm going to start by taking away the minus 1 in the numerator. And I am then going to take away the plus 1 in the denominator. And this is the same as 1 over 3n squared. So in this b of n, we know is greater than our a of n, and that matches up with this, so we know we can use that. And then this series converges by p series. So we can then say that our a of n squared minus 1 over 3n to the 4th plus 1 converges by direct comparison. Now here we have a possible FRQ question. So consider the series from 2 to infinity of 1 over n to the p times ln, of n, where p is greater than or equal to 0. So show that the series converges for p is greater than 1. So our a of n is going to be 1 over n to the p ln of n. And our b of n is going to be 1 over n to the p. So now our a of n is less than our b of n. And for this series to converge by p series, our p has to be greater than 1. And so that shows that for our series, it converges for p is greater than 1. Now for part B, determine whether the series converges or diverges for p equals 1. Show your analysis. So when p equals 1, our a of n is going to be 1 over n ln of n. And our b of n is going to be 1 over n. Now in this case, our a of n is greater than our b of n. And this series diverges by p series. And since our a of n is greater than our b of n, we can say that 1 over n ln of n diverges by direct comparison. So therefore, 1 over n to the p ln of n diverges when p is equal to 1 by direct comparison. For part C, show that the series diverges for 0 is less than or equal to p is less than 1. So again, our a of n is going to be 1 over n to the p ln of n. And this time our b of n is going to be 1 over n ln of n. So our a of n is greater than our b of n, which is greater than 0. And this diverges by the integral test. And since our b of n is greater than 0, we can say that 1 over n to the p ln of n diverges by direct comparison for 0 is less than or equal to p, which is less than 1. Now an example multiple choice question is what are all the values of p for which the infinite series from 1 to infinity of n over n to the p plus 1 converges. So our a of n is n over n to the p plus 1, and our b of n is going to be n over n to the p, which can also be written as 1 over n to the p minus 1. And our a of n is less than our b of n. And for this series to converge by p series, the p minus 1 needs to be greater than 1. So when you simplify that, you get p is greater than 2. That is E.